All right, we are recording. So, today, eventually, we are going to be talking about matter, substances, properties. Let's see, what else are we going to be looking at? Various types of properties, okay? But first, matter. Can you see? All right. Matter itself is anything that has mass that takes up space. It is everything around us. It is the large buildings that we are in, all the way down to the small atoms that make up everything, even the gas, the air that we are currently in. Okay? Microbes. Everything has mass, at least that is typically around us. Table salt. Okay? I don't particularly like table salt myself, but it is matter. Each little granule has mass that takes up space. Now, table salt, no matter where you get it from, is always going to be sodium chloride. It's always going to be NaCl. It does not change in terms of its composition. No matter where you get it from, it will always be that composition, that ratio of elements coming together. And that basically leads us into substance. Matter with uniform and unchanging composition. Now, since it is unchanging, we call that a pure substance. As we just mentioned, salt and water is H2O. Salt and water are both pure substances because they are always composed of the same components in a defined ratio. If you drink purified water, okay, I know there are many companies that have purified water that they sell. Well, if you take one company's purified water and another company's purified water and sample it, well, it's not going to be different formulas or different makeup of water. It will always be H2O, no matter where you get it from. But not everything is a pure substance. Prime example is seawater. Okay, seawater is not pure because depending on where you obtain your sample, and sometimes these samples can be just a difference of a few hundred yards. You can have a composition that varies in the amount of water, the amount of salt, and other dissolved substances. Has anybody accidentally ever drank seawater? It's absolutely disgusting. It's hopefully never on purpose, but sometimes you kind of get forced to do it by Mother Nature. But
I was little, I
it's
tasted it, but I immediately spat it out.
It's bad.
As a kid, I was told it made me went insane, so I
Yeah.
spat it out. I was terrified.
If you look at, has anybody heard of the Dead Sea? Okay, its salt content is so high that at certain points you can actually float on it because the density is so high. So that is obviously going to be significantly different in terms of its ratio of contents compared to other locations. So we have properties of matter. We've got physical properties of matter. We've got chemical properties of matter. Okay. Told you we're going to talk about different types of properties today. Now, physical properties are characteristics that can be observed or measured without changing that composition of a substance. And a lot of times these physical properties are going to help describe pure substances. Again, because we don't want to change their composition. Some common, but not limited to, these properties include density, color, odor, taste, hardness, melting point, and boiling point. If you think about water, if water is ice, it still has a formula of H2O. We melt it. It now becomes liquid water. Still has a formula H2O. We then decide to boil it. It goes from liquid to vapor. Notice how I didn't say gas. And we're going to learn about the difference between gas and vapor, albeit small difference. We're going to learn about that a little bit later on. Turns into vapor, but that vapor is still H2O. It's still made up of water. What's really different is that the molecules are further apart than they are in a liquid. Sodium chloride against go with salt. We would say it's solid, white, at room temperature. Okay, those are all descriptions of salt itself. Now, continuing on with our types of properties, we have two terms, extensive and intensive properties. Let's start talking about extensive properties first. Extensive properties are dependent upon the amount of a substance present. Mass, length, volume are all some examples of extensive properties. Okay, so, pause your writing for a second. Let's say you want to, I don't know, drive a car, okay? First trip you take, or you attempt to take, you put about 2 ounces of gasoline in the car. 2 ounces. You learn your lesson, okay? You're like, what am I thinking? So you put in a gallon of gasoline. Okay, you still haven't quite learned yet how much gas you put in there. But either way, you start off with 2 ounces, and then you decide to go for a gallon. Which one do you think would get you the furthest in your car? The 2 ounces or the gallon of gasoline?
Yeah.
Kind of a no-brainer, right? Your car can only go as far as the amount of gas that you put into it, unless you have a battery power, Tesla, okay? But you can only go as far as the amount of electricity that you use to charge your batteries in there, okay? So that would be an example of extensive property, okay? It is dependent on how much you have and how much you'll get out of it. Now, intensive properties, there's a reason why I highlighted the in there, okay, in intensive properties. These are properties that are independent of the amount of substance present. And usually a single intensive property is unique enough to identify a substance. Intensive, independent. I suggest that you underline the word in intensive and the word in independent. Those are really simple ways for you to try and remember which is which. Okay, which property is which. A prime example of an intensive property being used to identify a substance is density. A lot of substances have their own unique density. Gold, for instance. No matter if we have a little pebble of gold or a large bar of gold, it will have the density of 19 grams per milliliter, no matter what. And really, no other substance will have that exact density. You might have some that are similar, but a lot of times taking the density of gold was a really good means to verify that gold that was being traded a long time ago was actually gold because of its unique density value. So this gets us transitioned into chemical properties. Chemical properties are the ability of a substance to combine with or change into one or more substances. Key word when we're talking about chemical properties is that word change into other substances. I guess that's multiple words. But change is really what I was emphasizing. Chemical properties are the ability to change. Because when you have a chemical reaction or chemical change, you no longer have the same substance you had before. When iron forms rust, okay, rust is no longer iron. It is now called iron oxide. Completely different substance. When copper turns green in the air, it's forming a patina. Okay? You know, has anybody ever been to the Statue of Liberty? Has anybody ever seen the Statue of Liberty? At least even in photographs.
I've actually been to the Statue.
There you go. So it's a green colored statue, when in fact, when it was originally built, it was copper. I mean, it still is copper, but it had that copper sheen to it. But over the years, as you see here, it's turned to what we know today. And it's natural for it to do that. Sometimes it's even, it kind of acts like a protective layer. Also, a lot of architects and a lot of, that use copper in their stuff want that patina. So it's kind of a decor deal. Yes, Dave.
The whole thing's made out of copper.
Mm-hmm.
Copper's expensive, right?
Well, you gotta think about how old it was back then. Are you trying to go steal the Statue of Liberty? Well, we got you on recording saying that, so
Really?
might be difficult to do that. Yes.
Like solid? Like I won't
No,
testify
it's not
against-
solid. It's hollow. Yeah.
I won't testify against it.
Yeah. I believe you used to be able to at least go up in the crown, and I don't know if it's open anymore. I've never even been in New York, so I don't know. I know at some point that was allowed.
I was too scared to go on top. So.
What? Can you? So I know that it kind of fluctuates from no go, yes go. So
Why would it be a no-go?
it honestly it just depends on certain circumstances. So it could be weather, exactly. It could be,
When I went, they allowed it because it was nice and sunny.
Yeah.
And warm.
and it could be other reasons, like right now, maybe not because of congregations of people going to Ellis Island and getting up there with the whole COVID and everything like that. So it could be just like that. But also the inability for a substance to change into another substance is also a chemical property. When we place iron, again, we just saw that iron can turn into rust in air. If we place iron into nitrogen gas and kind of seal it up, we find that actually nothing occurs. It's still iron. There's no rust forming. In fact, a lot of foods are actually packaged with a blast of nitrogen gas. Potato chips are a good example. Nitrogen gas is pumped in there to do a few things. To provide a kind of a cushion from the product inside, but also to extend shelf life. Because nitrogen gas is kind of like in what we call inert gas to some extent. It doesn't react with a lot of stuff. And so they put it in there, protects it from being crushed, but also extends that shelf life. So it still tastes and looks tasty to you, weeks after you've purchased it, possibly. So as soon as you open it, it's actually nitrogen gas that is coming out. So changes of matter. A substance can change form. And so chemical properties can change with specific environmental conditions, including temperature, pressure. We'll talk about pressure here in just a little minute, but let's stick with temperature now. Again, water is really easy to discuss in terms of changes, so we're going to continue using that. At room temperature, water is a liquid. It has a solid, or not solid, it has a normal density, that's what I wanted to say, of 1.00 gram per cubic centimeters. But as we heat it up and get it to boiling temperature of 100 degrees Celsius, we find that it is now a vapor, or actually vapor would be a more appropriate term than gas, but gas is not necessarily incorrect. But again, we'll see today the difference, slight difference between gas and vapor. But now that it has turned into a new state, is now has a density of 0.0006 grams per cubic centimeter. So again, properties can change. We alter the temperature, we change the property. Now, let's talk about how we can change pressure. Okay? If you are cooking or baking, yes, there is a difference. Pre-packaged products. A lot of times you're going to notice that there'll be a little disclaimer on there saying if you are cooking at higher altitudes, you need to adjust your cooking timer temp. Okay? Well, that is because individuals at higher altitude have less air molecules on top of them. Okay, even though we go like this, we really don't feel anything. Right now, there's currently air molecules pushing down on us. Okay? Not only on us, but on, say, your water back there. Okay? There are air molecules, atmospheric, which is really what atmospheric pressure is, pushing down on the molecules in that water bottle over there. But say you live in Denver. Well, Denver is known as the Mile High City because it is pretty close to a mile above sea level. So right then and there, those individuals already have a mile's worth of air molecules less pushing down on the water molecules that you're trying to boil. So imagine you guys are water molecules, okay? You are, for some reason, dogpiling on Allie, okay? She's on the bottom, you're dogpiling. Let's say we take half of you off because you are now at a higher altitude. It may still be a little difficult. It's going to require some energy input, but it's not going to be as difficult to break free for Allie from that pile that's been reduced. And so when you try to boil water at a higher altitude, it doesn't take as much heat energy to cause it to boil because there's less weight holding it down. The problem is it often takes food longer to cook because, yes, the water's boiling, but it's still boiling at a lower temperature. So typically when you go to environments like that, plan on having a little more time in your cooking process to take that into consideration. Okay. All right. Now this last portion of the notes will probably be repetitive to years back all the way till maybe 4th grade. But we still need to know it because a lot of times we need to be able to classify matter into certain groups when we're talking about chemistry. So we need to talk about the states of matter. These are the physical forms of matter, including solid, liquid, and gas. And really, we can differentiate the three by the way that they fill a container. And yes, there is a 4th state of matter that is recognized by scientists, and that is plasma. But there's only one entity that produces it naturally on Earth, and that is lightning. Lightning is the only natural producing source for plasma. So we're going to talk about these 3 types of matter. And then we'll end with talking about how these types of matter can, or these states of matter, can change through various processes. We'll start with solid, okay? Solids have their own definite shape as well as volume. In solids, the particles, yes.
Oh, it's just a leak.
Yeah, I see a drip coming down from
It finally happened. That's all right. You can move that if you need to. You might want to move your stuff. I will. It hasn't happened yet this year, but we haven't quite had the snow that we've had yet. So I'll just do this for the time being. Can you still see back there? Okay. Okay. Anyway, solids, as we said, that we can distinguish between the three states of matter by the way they fill a container. Well, solids will not conform to that shape. They are too tightly packed. They have a definite shape, okay? And they are incompressible. We try to compress them, well, they're not. And they will essentially just splinter off or shatter, depending on what type of material it is. Wood, iron, paper, sugar, there's a lot. I mean, your desk, okay? Those are considered to be solid materials. But, you know, solids can do more of other things than liquids or gases can. For instance, sound can travel faster through solids because of how their particles are situated. The sound is really just the event where molecules vibrate and move and hit their neighboring molecules. Well, these are so tightly packed that that whole process goes really quickly. In gases like here, the molecules have to travel relatively larger distances between them to interact and continue the movement of that sound. You caught up? Almost. Okay. I'll let you get caught up. Go ahead. Do I have it lined up right? Okay, good. Yeah, there's been years where that's leaked like a sieve. We've had so much snow, obviously, this last week. Cold temperatures can cause there's sealants up there where like the HVAC units are. It can cause it to expand and contract, and really the amount of water sometimes just kind of overwhelms whatever they already have up there. So I get these little drips every once in a while. So it's fun.
So we should start bringing umbrellas.
No, it only happens right there, actually, typically. So, all right, liquids. Defined as matter that flows, has constant volume, and will take the shape of the container. The molecules or particles in a liquid are not as rigidly packed together or held in place as they are in a solid. Which, because of their looser packaging, if you will, they are allowed to flow past one another, which gives them that fluid appearance. Now, in most liquids, the particles will expand when heated. I said most. Okay. Think about water. What happens when water is cooled past freezing?
It condenses.
It expands. That's why whenever you put something that is water-based in a freezer, you got to be really careful that you don't fill it too hot. Does anybody ever put a soda in the freezer? Yeah? Did you ever forget about it? What happened? It exploded. Yes.
Okay, have
I don't know. You haven't said it
You
yet.
take your little ice cube maker things down my mouth.
The ice cube trays?
Yeah.
Yep.
You take Dr. Pepper, you pour them in there, right?
Okay.
You freeze them. But they don't taste like Dr. Pepper when they're frozen.
No, I've never done that.
Water down, probably. It's like water. But there's no water, you know?
Yeah, there is. Yeah, soda's basically syrup and carbonated water. And so what could be happening is the syrup and whatever other substances, they might be condensing, while the water, as you'll see when you make it, it looks as though that it's got kind of a clear outer port. That's because the water has expanded. So it might not taste that way because you're currently or initially tasting water. Whereas if you kind of just like let it continue to thaw, and then you might start to see a more familiar taste.
Like water down soda sucks.
Yeah, it's not very good, no. Now liquids are what are they're considered to be virtually incompressible. Now it doesn't say incompressible; it says virtually incompressible, because you can argue that because they are more loosely packed than solids, that there might be just a very minute amount of space for them to move where you can compress it. But really it's so small, if at all measurable, so we can't really rule it out that it's incompressible. But we often use that ability for liquids to take the shape of their containers but be virtually incompressible to make our lives easier. Hydraulics. Okay, we use hydraulics in, almost every day. If you drive, you might have hydraulic shocks. Might be gas filled, but also might be hydraulic. Or if you use certain machinery, you're going to have the use of hydraulics. Last, we get to gases. It's a form of matter that flows to conform to the shape of its container, fills the entire volume of its container. So gases are the only one that will expand to fill whatever container they are placed in. This time, the particles of gases are relatively far apart. That's what then allows them to be easily compressed because of that space. Neon, methane are all examples of gas. Now, I was mentioning earlier that gas and vapor, albeit are extremely similar and often used interchangeably, that there is a difference between them. And that is the fact that a vapor refers to a substance that, when at room temperature, is either solid or liquid. Oftentimes it takes heating up for it to turn into a vapor or a gas state. So gases are gases naturally at room temperature. Vapors are either solid or liquids at room temperature and require heating. And last but not least, we have the changing of matter. Now, matter can change between all three states. Water is a very good example. It could be frozen solid, it could be liquid water, it could be gaseous vapor. And this is a form of physical change. Changing state is not chemical change. Physical or state in the let me rephrase that. Change in state, there we go, is an example of physical change. Now, a lot of times you go solid, liquid, gas, or gas, liquid, solid. Okay? Solid to a liquid is melting, liquid to a solid is freezing. Gas to liquid is condensation, and liquid to gas is vaporization. These are terms that are very important to know. But sometimes you can completely bypass that middle liquid state. You can go from either a solid to a gas or a gas to a solid. If you go from a solid to a gas, it's called sublimation, and a gas to a solid is called deposition. Prime example is dry ice. Dry ice is solidified carbon dioxide. As dry ice goes from its solid to a gas state, it's basically going back into its natural form. So it is subliming as it does that process. Yes.
There are a couple spots that I didn't get out.
Okay, let me pause the or let me stop the recording, then I'll go back to them, okay?